All right, gentlemen, how's the homework?
Well, it's homework.
Still on the back burner?
Yeah.
All right, well, I won't hassle y'all. Yeah, I'll be at a meeting tonight, so I won't be able to interact as quickly as I'd like to, although I'm not perfect at interacting after 5 anyway. Today we're going to talk about the electron spin. I've talked some about spin, right?
Yeah.
So what do you know at this point about spin?
Orientation. Yeah. It's quantized. It determines the orientation, whether it's positive or negative.
That's not how you spell determines, I'll pretend, but. What is it representing?
Angular momentum. Is that right?
Okay, that's our preconceived notions. Now let's go through and get some details on it. So here is a picture showing the emission spectrum from a hydrogen atom. You have the Lyman series of emission lines, which are not shown in my picture here, but are ultraviolet emission. The Lyman series is caused by electrons falling from n higher than 1 down to n equals 1. Because remember, n equals 1 was minus 13.6 electron volts. N equals 2 is that number divided by 2 squared. So take that and divide it by 4. Well, 13.6 divided by 4 is going to be 3.4. Right, 4 times 4 is 16, 4 times 3 is 12, add 1, 13. So the smallest energy is going from 3.4 to 13.6. That's a 10.2 electron volt difference. So this one here is energy equals HF equals 10.2 electron volts. And all the rest of them are higher energies. Now, a visible photon is going to be under 4 electron volts. I think maybe under 3 electron volts. So we're talking far ultraviolet here. So you're not going to see that with your naked eye. Then we have the Balmer series. The Balmer series is going from, 13.6 divided by 9 is 4.6, 1.5 roughly. So the smallest of the Balmer series is going through a difference of 1.9. And then the largest would be going through a difference of 3.4. That's the visible spectrum right there, in a nutshell. And then if you go to the Paschen, the largest energy for the Paschen series is going to be 1.5 electron volts. That's infrared. So you have, and the bracket, of course, its largest one is going to be 16, 30.6 divided by 16 is, I don't remember the number, but not very big. So you have the energies, and this gives you the visible spectrum. All fine and good until you look at it more carefully. When you look at it more carefully, you see that what should be one discrete line is actually 2. And so this is called the fine structure. The fine structure is this splitting of one line into 2. And so how do we explain this fine structure? So scientists thought about that for a minute. This picture here is actually showing how we explain it, but we haven't gotten to that yet. Instead, we take a ride in classical physics. In classical physics, the Earth orbits the sun. So what we're doing is taking an analogy to the planetary model. Remember, Rutherford came up with the planetary model that says that the electrons orbit the nucleus like a planet orbits the sun. And so as the planet orbits the sun, we have an angular momentum associated with the planet going around the sun. And so angular momentum is going to be the mass of the Earth times the radius of the orbit times the speed at which it's going around circle, right? That's R cross P. P is mv, and R is, of course, R. And if we approximate to doing a circular orbit, then it's just R is perpendicular to P, and R cross P is R times P, this equation. So that's the angular momentum of the orbit. But we know that the Earth is also spinning on its axis. An axis that, by the way, is tilted 23.4 degrees roughly from the axis that we're orbiting the sun. And so we have an angular momentum that's in a different direction that's associated with the Earth spinning. In that case, we use the I omega form to find the angular momentum. And so treating the Earth as a solid uniform sphere, then I is 2/5 mr squared. And then we have omega for the spin, where omega is the number of radians per second of our spin, which you can quickly calculate. We do 2 pi radians in almost 24 hours. If you care, it's in a sidereal day, we do 2 pi radians. The sidereal day is 23 hours. I can't remember it's like 56 minutes and some seconds. Not important for today's lecture whatsoever. So we have 2 pieces that make up our total angular momentum. So the Earth's angular momentum would be L orbit plus L spin to give us our L total. And so the scientists said, well, why can't an electron orbiting the nucleus have the same components? Why can't the electron have an orbital angular momentum? What we've already calculated, L orbital is equal to h bar square root of L times L plus 1. And of course, we have the amount in some randomly selected z direction is h bar m sub L. And then it could also have some spin angular momentum. Makes sense. I have no problem with that. But then we go a step further. Classically, I thought I had moved this so it didn't clobber. Classically, you have a magnetic moment if you have a charged particle spinning. And that magnetic moment that's Q over 2m. So the charge of the charged particle divided by 2 times its mass times the angular momentum. That's its orbital, that's the magnetic moment produced because it's going around a circle. And of course, I've dropped off the circle part when I say angular momentum orbital. It could be doing an elliptical path. It still has the same angular momentum. It's still going to have the same magnetic moment. More generally, we take this term here and we call it the gyromagnetic ratio, gamma. So in this case, gamma was equal to Q over 2m. The reason we call it gamma is because when we get to a solid object rotating about its axis, i.e. spinning, gamma is going to have a slightly different value. So scientists said that the electron must have a magnetic moment based on its spin. And because it's charged, it's going to have, it has a magnetic moment based on spin and its charge, as well as its orbit. So you have 2 different things that give it a magnetic behavior. And if they're aligned together, that's going to be lower energy. If they're anti-aligned, that's going to be higher energy. And so you have slightly different energies depending on the orientation of the electron's angular momentum compared to the orbital's angular momentum. And that would perfectly explain why we have this split. And so they said the electron must be spinning, and we can calculate its angular momentum for its spin based on this relationship. And that matches exactly with what you guys said here, that the spin represents angular momentum. Only problem is, it ain't right. It sounded oh so good, but it turns out that we have been able to determine the size of the electron is no bigger than a really tiny size. And for it to be able to make the magnetic moment that we observe for the electron based on that spinning, it would have to be spinning so the exterior of the electron is going faster than the speed of light. Well, that violates some other rules. And so the conclusion is it's not spinning. It simply is an intrinsic magnet. It's something that's built into it. So now, this intrinsic magnetic moment that I have here in purple for you, and now highlighted in purple, so it looks like the Lakers, except for the yellow on purple looks black. Sorry. Ruins the whole Laker effect. Or Minnesota Viking. Little point of fact. Why do the Minnesota Vikings and the Los Angeles Lakers have the same colors?
I actually don't know either. Did the Lakers?
The Minneapolis Lakers had the same colors as the Minnesota Vikings, yes, because they both played in the same town. Another little point of fact, why do the Vikings even exist?
I'd like to hear this one.
Because the American Football League awarded a franchise to Minneapolis, and the NFL, to fight the AFL, put a franchise in Minneapolis as well. So then the AFL rescinded the franchise in Minneapolis and moved it to Oakland. So the Oakland Raiders were initially supposed to be in Minneapolis. Final question. When I was in college, the Los Angeles Kings wore the same colors as the Minnesota Vikings. Why? Because they shared the same stadium with the Lakers, who all tied together. But then they changed their colors to match the Raiders because the Raiders moved down to Southern California. So that has a lot to do with quantum mechanics. Sorry.
History lessons.
About things that you will never be asked about.
The Green Bay Packers.
The Acme Packers. Come on.
Yeah.
I believe that's what they were at one time. When I was a kid, I read all about the history of the NFL. Let's just leave it at that. Okay. Spin is now an intrinsic value. What that means is it's not possible for us to have a wave function for spin. All of our Schrodinger equation stuff cannot be applied to spin because it's just an intrinsic property. So instead, we are forced, I say forced because, I far prefer to use the linear algebra techniques of Heisenberg. We're still going to pretend that there's angular momentum involved because all of our angular momentum rules are going to apply because those angular momentum rules, we're really talking about our magnetic moment relationships. So all of our commutators and what are still going to apply. So that means we have the ladder operators, the whole 9 yards. Our particles that we're dealing with, if we were to look at equation 4.119, which I did not bring out specifically in my lecture last class period. It's on page 165, I believe. Yeah, 165. When we found the eigenvalues for L squared, it turns out that it's consistent if you have integer values for L, which we already had. It was a requirement we already have. Or if we had half integers, if you had L was equal to 1/2, 3/2, 5/2, that would also have been consistent. So there's only two possibilities, integers or half integers. And it turns out that the electrons are half integers for their spins. Every single electron has a spin of plus 1/2. Most people say, wait a minute, you have spin up and spin down. One's 1/2 and one's minus 1/2. This is the S value. Remember, for the orbitals, we had L and M sub L. And the L values were like 0, 1, 2, 3, 4. And the M sub L's, which only exhibited if we were in a magnetic field, went from minus L to plus L. For spin, we have S, which is always equal to 1/2. And then we have M sub S, which goes from plus S to minus S, which is only going from minus 1/2 to 1/2. There's only two options there, but it's following the same rules. So when we talk about the spin, nobody ever talks about this one because it's the same for every single electron. By the way, it's also the same for every single proton. It's the same for every single neutron. Protons, neutrons, electrons, they all have the intrinsic spin of 1/2. And we call them as a group fermions, named after Enrico Fermi, who along with Dirac, Paul Dirac, I believe, worked out the mathematics of how they behave if they have 1/2 integer spins. So we only have two possible spin states. So if I have two possible spin states, I'm going to have some let's talk about my spin in the z direction operator. My spin in the z direction operator is going to have two eigenvalues, 1/2 h bar and minus 1/2 h bar. I should write this a little differently. So I have those two eigenvalues. How could I make a matrix for the operator? Such that I have S sub z acting on some eigenstate chi is equal to lambda, and I'll put lambda, I'll say that's chi plus, and this is lambda plus chi plus. That's supposed to be a chi. It looks more like a C now, or a psi, I mean, there. How do I make this operator matrix?
Isn't it the using the subtract or S sub Z minus your lambda?
Okay, and that is, that's how the textbook actually goes through and does it. But there's an easier way. If you have this relationship, so you're dealing with the eigenstates of the operator, then it's going to be diagonalized. Remember, we went through and we took non-diagonalized operators and said, what are the eigenvalues? Now we can make the diagonalized operator and find the eigenstates of the diagonalized operator. We're jumping straight to that because that's where we're starting. So I'm just going to put the eigenvalues as the diagonals and zeros everywhere else. So I'm going to put h bar over 2. Go ahead. What are you saying?
I was saying what you're doing, so then zeros in the offset in the other corners.
Yep. So now my handwriting there was pretty poor. Here's how I'm going to make my handwriting better. I'm going to put the h bar over 2 outside and 1 and minus 1. That's easy. And what are the eigenstates of this vector? They're actually implied by the fact that I made that vector.
One and
1 and 0. If you have a diagonalized eigenstate, then you're going to have just 1, 0, 0, 0, 1, 0, etc. And the way to get the plus and the minus is just by looking at, or the 0, 1, 1, 0 is looking at which one goes with which. So I had the minus was in the lower spot, so that's why the chi minus is 0, 1. So here we have These things here are called the spinors. Those are our eigenstates for spin. And this is our S sub z operator. That wasn't hard, was it? Now, here's where I have some rules for us. The S squared value has the same eigenvalue equation, except for you're replacing L with S. And the S sub z has the same eigenvalue relation, except for you're replacing M sub S for M sub L. So there's nothing new and special there. You always have a total angular momentum of 3/4 h bar squared. Well, you have to square root this because that's S squared. So S is always equal to square root of 3/4 h bar. That's always the total angular momentum associated with the spin, because it always has a spin of 1/2. But the orientation is the part that you think about as the spin, because that's the one that has two orientations. So I didn't do this one here. Can you give me a good reason why I didn't do that one? I can. We had the S eigenvalues were both 1. It was very boring. Actually, it's not 1, it's square root of 3/4 h bar and square root of 3/4 h bar. But they're the same, it's very boring, so I didn't want to do it. But here we have S sub z. This one we've made. We saw how we came to that. The spinors, these are 3 different ways of writing the same thing. Chi plus, I've been putting it inside a ket to make it clear. An arrow up. That's usually my preferred way of indicating the spinor. Arrow up versus arrow down. What does this middle one, what do we actually put in there? What's the 1/2 plus 1/2 or 1/2 minus 1/2? Okay, M sub S is the one that can have negative, so it's the second one. The first one is the one that's always 1/2. So it's writing it as S M sub S. So all 3 or all 4 of these are equivalent ways of writing the same thing. And this top one is all spin up. The bottom one is all spin down. So you'll see it different ways. Depends on the mood I'm in, depends on the mood the author's in. But my preference usually is this. If we're doing linear algebra, obviously I'm going to use that. I don't like this one except for when there is a specific reason for it, because it's more bulky to write. Now the ladder operators. We had ladder operators before, and it's the same definition. We had L plus minus equaled L sub x plus or minus I L sub y. So for S ladder operators, it's going to be the same thing. But that's built out of the Sx and Sy matrices. What are the Sx and Sy matrices? You what?
Like their actual values.
Well, what do they even mean? Yeah, we want to get the actual values. What do they even mean?
Would just be X and Y components.
It'd be the X and Y components of the spin. Now, the spin, when I talked about angular momentum, I said that the M sub L didn't have any meaning unless you're in a magnetic field. The M sub S cause that splitting, the fine structure, even if you're not in an external magnetic field, because you have interaction between the magnetic moment of the orbital and the magnetic moment of the electron. And so there actually is some meaning to these M sub S's, even if we're not in an external magnetic field. And by extension, the M sub L's, because the M sub L and M sub S are tied together in their meaning. So when we start talking about an atom with its 4 quantum numbers, even outside of a magnetic field, M sub L and M sub S do make a difference because of the interaction between the spin of the electron and the orbit. We call that spin-orbit couplet, by the way. So the M sub L and M sub S now do have a way of manifesting even when we don't have an external magnetic field. And the SX and SY are telling us to orientate, how much the magnetic field is in the directions perpendicular to SZ. So we're going to use these to try to find the relations. So S plus acting on, I'm just going to put an up arrow. How's that? S plus acting on spin up. What state do you produce if you're in the M sub S is equal to 1/2 and you put the operator that's going to raise it by 1? What should this M sub S be if you raise it by 1?
Because you can't have anything higher than 1.
Right, so that has to equal 0 because you can't have anything higher. You answered perfectly. And S plus on 1/2 comma minus 1/2 is going to equal, and that's what I have right here, H bar over 2, 1/2, 1/2. And then what that means is one half, that's the one that was 1, 0. It gives me that relationship, which means A equals 0 and C equals 0. Right, because if I multiply it through, I'm actually going to multiply it through. I know you guys can do this. This is equal to A times 1 plus B times 0, and then C times 1 plus D times 0. And so that's what gives us so that's what I get by applying this rule. By applying this one, I'm going to have that relationship. So multiplying through, I'm going to have those two. So now I can make my entire matrix then. S plus is equal to 0, H bar over 2, 0, 0. So there's my raising operator. And then for my lowering operator, I have this equation here. And that's got the minus sign, right? Yeah. And using the same logic that Indy used before, if I use the lowering operator on the lower spin state, it gives me 0. So doing the same type of work, a new A, B, C, D. So that gives me A equals 0, C equals minus H bar over 2. And then doing the second relation, gives me B and D is 0. So that means my S minus operator is equal to 0, 0, minus H bar over 2, 0. So I've got my S minus and my S plus operators built from those eigenstate relations. So now I can come over here and say, well, S plus plus S minus is equal to 2SX. Right, because if I do S plus plus S minus, each one has an SX. And then the ISYs are going to cancel out. Well, they'll add out to 0, excuse me. And so SX is equal to 1/2 S plus plus S minus equals 1/2 of 0 H bar over 2, 0, 0, plus, come on, 0, 0, minus H bar over 2, 0. So there's my SX. How do we find SY? Do what? Okay, one way of doing it is by subtracting them. S plus minus S minus is equal to 2I SY. And so if I do that, the only difference is that I'm going to be dividing by 2I, and I'm going to have a minus sign here, so it's going to turn out that this is a positive in that corner. So I'll have SY is equal to So assuming I made no mistakes, those should be my SX and SY operators. Work out?
Did we negative IH bar before?
Yes. I dropped off the I on bottom and forgot there's still a 4. So we have these things that we call the Pauling matrices, and I have a problem somewhere because I was thinking about that. I have over 4s. Yes. No. Yes. No. I have over 4s, and they're supposed to be over 2s still. Also, I have my sign wrong. Oh no. How did I get my sign wrong? Gentlemen, I feel horrible. I'm going to make sure that these two equations I wrote down to start with were the correct equations, because I don't see how I could have gotten the signs wrong if those are right. S plus, oh. Okay, so there's no over 2's here. So there's where the factor of 2 comes in. That's going to correct those to 2's instead of 4's. But that's only one of my 2 mistakes. S minus on X plus is H. Okay, there's my other mistake. Those are both plus signs. I took the SZ rules instead of the S plus and S minus rules. That's where I made my mistake. So that takes care of the sign errors. I'm not going to go and redo it because, well, it's more time than it's worth. You can see how it's going to follow through. That is something I am sorry about. The method was all perfect. The starting equations I put in incorrectly. So that work then gives us matrices that are famous. These are Pauli's matrices. S sub x is equal to h bar over 2 sigma x. S sub y is equal to h bar over 2 sigma y. S sub z is equal to h bar over 2 sigma z. And I believe that these Pauli matrices are given, yep, the front cover of our textbook. So those are our matrices that we deal with for spin relations for calculating eigenvalues. Now let's do one more thing before we move on. What do you suppose the eigenvalues are going to be for Sx and Sy? If you were to guess, what would they be?
I'll maybe guess H bar over 2 or H bar, something with an H bar in it.
Okay. That's what I would have guessed too. Actually, I say before we go on, that's my last slide. Let's actually calculate them. So Sx minus lambda 1 that's the relation we use, right? Our eigenstate relation. And then we say determinant of Sx minus lambda 1 equals 0 equals, so for Sx, I'm going to have the h bar over 2. Well, I got to put it inside here. It's 0 minus lambda, h bar over 2, h bar over 2, 0 minus lambda. So that determinant's really tough. You were exactly right with your guess, Indy. Yay! Well, here's how we could have said Indy had to be right. What's special about S sub z? Answer, nothing. It was an arbitrary designation. So we could have just as easily called that x. So you have to have the same eigenvalues as you had for x. Now, or for x and for z. What about the eigenstates? What are the eigenstates for this operator? Lead me through.
So, writing out the matrix SX. What's your, this is the problem. So we got, the first one is, H bar over 2 and B.
Let's make life easy. Let's make life real easy. Yeah. I hate to write that so many times. Okay, so now what?
B equals A, and A equals B. So,
What should I have here for my vector?
um, 1, 1.
But I have to have a normalization constant because it has to be normalized.
Yeah.
And so then to normalize it, A star 1, 1 times A 1, 1 is equal to A mod squared times 1 plus 1. But that had to be 1, so what is A equal to? And that's, of course, just taking the real option because there's a plethora of other options I could have taken. So there is my eigenspinner for the SX. What about for the SY? Oh, wait. That's for the lambda plus. We need to do it for the lambda minus. What's it going to be for the lambda minus?
So B equals negative A and A equals negative B.
Yeah. You can see the end from the beginning. And so I'm going to have 1 over root 2, 1 minus 1. I know it's 1 over root 2 because it's still 1 and 1 effectively, right? The sign changes, but the magnitude's the same, so it still has to have the same. And then finally, as a test, how should these two relate to each other, this one and this one? They should be orthogonal. So this one here we call C parenthesis X on top minus, and this one, or C, it's chi. Parenthesis X on top plus. So chi without the parenthesis is for Z. Parenthesis X, parenthesis Y is the spinners for X or for Y. And so we should have and so we do that by putting and sure enough, they're orthogonal. I mean, this is not hard stuff. I'm doing it just to reiterate the rules that we've learned to make sure, yeah, these still apply and they're still true. And, remind you how to do it as well. Now, that was for SX. Can we do that for SY? Sure. The only difference is you have I's and you're going to have a plus or a minus where you had a plus before. So we have 5 more minutes. Let's quickly look at the homework, which I trust I put here. Yay. Use calculus to find the most probable radius for the electron, the hydrogen atom in the ground state. So let's break it up into two pieces. A, R most probable. How do you find that?
Well, that's your math.
Yes. So if we put if we plot this, we have something that goes like this, and that's going to be right here. So how do we find that?
Well, with calculus, you can take the derivative of that and set it equal to 0.
What are you plotting here? What is that line? I called it the probability, but what is it in terms of our wave function?
The probability of the electron being at that radius.
Yes. In terms of our wave function, what is that?
Oh, yes, I understand.
Almost. There's more to it. Yes.
Oh, yeah, because we're in circle.
Because this was only with respect to radius. So we had to take into account the other two dimensions. So that's psi mod squared 4 pi r squared. Now this is the ground state. So for the ground state, psi 100 equals, and you can look in your textbook. Your textbook gives you psi 100 as well as many other psis. On okay, those are the r's. Where's the psis? I know it has it because that's where I got it from when I did my solution. Psi 100, by the way, is very simple. Okay, equation 480 on page 151. So that's the wave function we're using for this. Obviously, I could have given you harder ones, but as I said in class Monday, why give you something that's harder? It's the mechanics that I want to make sure you have down, not being able to do hard math. That's why you're taking differential equations in linear algebra.
Yeah.
Okay, so that's how we do the first one. So you're just going to take that psi 100, psi mod squared times 4 pi r squared is this function. You're going to take the derivative out with respect to r, set it equal to 0. But then there's a second portion to this problem, the expectation value for the radius. So how do you find the expectation value?
So then you do that side, the conjugate side, or the integral, yeah. Conjugate side with the r in the middle, times r times side.
Okay, well, I'm going to put here dv originally, but then that's going to be equal to, because r is a simple thing, and there we have the dr, right? So this here is the same thing that we did the derivative of before, which is why I organize it that way. Now notice we have r times r squared, so it's going to be r cubed. Boom, you do that, you get your expectation value. And like I told you, you can find this done all over the place. The answers are very simple. They're both going to be answers that are just a times a constant, where a, going back, was defined as the Bohr radius. That was on page 150. A was defined for us.
Right.
Number 2, calculate the commutators. Yep, have fun. I've done half of them already in class, right? And for all of these, you're not going to have to invoke psi because you're never going to get to the point of having to calculate a new commutator. You're just going to expand and say, oh, I have a commutator of these. Well, I already know that answer. I have a commutator of these. I already know that answer. And so you don't have to there. Number 3, use the techniques developed in this chapter to discuss. You do not need to solve. I'm not asking you to solve this problem. Just talk about the methodology you would have to use to solve it. And yeah, I think this problem is solved in the textbook. How you'd find the solution to the 3-dimensional harmonic oscillator problem with the Hamiltonian shown here. So remember the normal harmonic oscillator, we had X here instead of R. And we found that solution. So now it's going to be R. So it's a 3-dimensional problem, right? The momentum is a 3-dimensional, the R is 3-dimensional. So it is a different problem. And so you need to go through and say, first, do this. Second, do this. Third, do this. And explain the process of how you'd go through and solve it, right? So this is making sure you understand the process of finding the solution without having to do all the nitty-gritty work.
Okay.
All right. So have fun with the homework.